All right, Chemistry 3101. We left off looking at these questions, and we didn't solve question 15.39 B and C. We left those ones out yesterday, so let's take a quick look at them. And it says for each pair of compounds, identify how you would distinguish them using either NMR spectroscopy or carbon 13 NMR spectroscopy. Well, if we take a look at this one here, so if we take a look at this compound here, and we think about protons, so we'll start with proton NMR for this one. So I'll put here proton NMR, and how many signals will we see? Well, we know we have a proton back here, right? There's a proton back here, and there's a back here. So we have those three protons. Is there an axis of rotational symmetry? Um, you could rotate that, but you're going to end up with something different because the two chlorines are going to be going in the back. But you see that if you did the replacement test, right? If you did the replacement test with this one and this one, what you would end up with in that case would be a pair of enantiomers. So those two protons are enantiotopic. And so since these two protons here are chemically equivalent, we're actually only going to see two signals in the proton NMR, two signals in this one. Whereas in the second compound for the proton NMR, we do have, we have a proton coming up here, and then we have a proton coming down here, and we have a proton coming down here. And so now, if you did the replacement test, you would end up with a pair of diastereomers. And so each one of these protons is unique. Even if you didn't understand what diastereotopic meant, you can see that all three of these protons are in unique environments. And so we would see three signals for this compound, three signals in the proton. And it's for the same reason that we would see two signals in the carbon 13 for this compound, right? This carbon and this carbon are chemically equivalent, whereas this carbon is unique. So we see a total of two signals for this one, and the same thing here for the carbon 13. Each carbon is unique, and so we would see a total of three signals. All right. The next one I think is a little more straightforward, um, kind of stuffed in here, but you see we have an alcohol, so this compound, and then we have an ether over here. Well, as far as the proton NMR goes, I mean, the easiest way to tell the difference between these two is for the alcohol proton, you would have a broad singlet, somewhere between what did we say, 2 and 5 parts per million. Whereas that's going to integrate for one proton. And then for the proton over here, I mean, you don't have that broad singlet. You have a singlet that's going to integrate for three protons. So singlet, and where would that come out? Maybe around 3 parts per million or something like that for an ether. So I'll put here 3 to 4 parts per million, maybe. But anyhow, I'll just write around 3 parts per million, and that's going to integrate for three protons. The carbon 13 might even be simpler for this one because there's a different number of signals, right? In the first compound, there's no symmetry in it anywhere. So in the first compound, you get 6, 7, 8, 9, 10. You get 10 signals. But in this one, you get 11 signals. So it's kind of not a goofy question, but anyhow, I think you all would have picked up on that really quickly. So there you go. That's how you would tell the difference between those compounds using proton or carbon. But let's try something a little more interesting. And let's take a look at this question here. So this is 15.57C. And given our molecular formula, so given this molecular formula, we have an HDI that is equal to 0. If you remember, a saturated hydrocarbon has the formula CnH2n plus 2. Well, if you have 4 hydrogens, 2 times 4 is 8, plus 2 is 10. So obviously, this thing is fully saturated. And so if we have an oxygen in our molecule and it's fully saturated, we saw this yesterday, the only possibility is that we have an alcohol or an ether. And so what we would do is go ahead and look at all the signals here and look for a singlet that integrates for one proton. And if we have a singlet that integrates for one proton, that's probably an alcohol. And if we don't have that, then it's probably an ether. And you notice that we have something around here. Okay, so we have this at 3.92 parts per million, we have a singlet that integrates for one proton. So I'll just put here alcohol with a question mark, right? Because alcohols come out between 2 to 5 parts per million. So that's a good candidate. Now let's take a look at the rest. At 0.9, we have 6 protons that give us a doublet. So what does that mean? I mean, really the only possible way that could happen would be to have 6 protons that are chemically equivalent like this. So that means they're attached to a carbon with 1 hydrogen, right? If there's free rotation around this sigma bond, all 6 of these protons are coupled to 1. So it's going to give you an integration of 6, but you only get a doublet because you follow the rule neighbors plus 1. Well, you have 1 neighbor plus 1 gives you 2, gives you a doublet. Give me a thumbs up if that makes some sense to everybody. So how I figured out that you have something that looks like this. Okay, cool. All right, so that's kind of my first rationale, is that I have some kind of piece like this. It doesn't necessarily mean it's an isopropyl, okay? It could be an isobutyl group too. It could be a neopentyl group. It could be lots of different things. But anyhow, then at 1.76, we have a multiplet that integrates for 1 proton, and at 3.38, we have 2 protons that give us a doublet. So that means that these 2 protons are split by 1 proton. So what does that mean? It means we have 2 protons that are split by only 1 proton, like that. Well, you're starting to see that if there's only a total of 4 carbons in the compound, that this CH and this CH must be the same one, right? Because that would give you a total of 4. And so, you know, if you're picking up what I'm putting down here, what I'm saying is that this piece must have to go here, right, on top of this. Now, it's kind of silly the way I'm doing it, but I'll just redraw it. So if we have something that looks like this, and I'll draw it in black here, if we have CH3, our methine, CH3, and then a CH2, and if we had an alcohol like this, then this explains why this proton, okay, integrates for 1, but it gives you a multiplet because it's split by how many? It's actually split by 8 protons. So if you have neighbors plus 1 and you have 8 plus 1, 8 plus 1, that gives you 9, which would be what, a nonette? But that might be kind of hard to see. You know, that's a lot of splitting, my friends. And so, you know, maybe a multiplet would be more appropriate for that. So this is really the only possibility. So if we label these as A, B, C, and D, we'll practice our annotation. The A protons would be these ones, okay, these ones here. The B proton would be this guy right here. The C proton would be this one, gives you the doublet, and then the alcohol proton would be the D proton, like that. All right, so you could call this compound, you could call it isobutyl alcohol, or you could call it 2-methyl-1-propanol. Either one is totally fine. And remind me when we do the final exam review, remind me just to kind of go over alcohol nomenclature with you, because alcohol nomenclature, if you understand the nomenclature of alkenes, which I know you're all really good at, trust me, you can name an alcohol with very little coaching at all. All right, so there you go. So the first compound was this ketone. This is called, I mean, there's a few names you could give this compound. You could give it the name 3-methyl-2-butanone, or you could call it isopropyl methyl ketone. The other one is this alcohol here. So this is called, this would be called 2-methyl-2-butanol. And the last one here, which we just went over, is isobutyl alcohol. All right, so there we go. So those 3 compounds are done. We solved this one. So let's take a look at this guy here, okay? It says deduce the structure of a compound with a molecular formula C6H14O2 that exhibits the following proton NMR spectra, IR spectra, carbon-13. So they gave us an IR, they gave us a proton, and they also give us a carbon. Come on, Mr. Dion. Carbon-13 down here. So they give us all the necessary information. You know, even before we look at the formula, anybody see any low-hanging fruit here that they are just, oh, I see something right away. Does anybody see anything just in the first 2 seconds? Exactly. Thanks, Isaac. Right? I'm sure that all of you looked at this before you even read the problem and said, well, you know, I don't need a lot of coaching. I can tell that there's obviously an alcohol somewhere in the compound, and I would say you're 100% right. Okay, there's obviously an alcohol in here somewhere. Okay, other functional groups in here, I would say nothing super abundantly clear. There is another functional group in there, but definitely an alcohol. So let's take a look here. So it says we have C6H14O2, And so that means we have an HDI that is equal to 0. So that means there's no double bond. So we figured out that there's at least one alcohol in the compound. Okay, if there's an HDI of 0, that means there's no carbonyls, right? And you can see there's no carbonyl here anyway. So that means there's no ketone, there's no aldehyde, there's no carboxylic acid, there's no amide. Okay, we can just forget all of that stuff. So we know for sure that there's an alcohol in the compound. Now, as far as other functional groups, we either have two alcohols or we can have an alcohol plus what? So we either have alcohol times 2, or could anybody tell me we would have an alcohol plus what? What would have to be the other functional group if we have an HDI of 0? What's the only other functional group that contains oxygen that has an HDI of 0? So it's going to be a functional group that has an oxygen in it, right? Because there's two oxygens, right? There's O2. So at least one of them is an alcohol. Exactly. The other functional group is an ether. Okay. So somebody said, oh, maybe is it aromatic? So here's how we could tell very quickly that it's not aromatic. Okay. The way we can tell it's aromatic, there's a few ways. Number one is that an aromatic ring has 6 carbons. Okay. It has 6 carbons like this. But if you have, there's no way you could have 14 hydrogens in 2 oxygens, right? Because you'd have to have, even if you had only one substituent, okay, like this, okay, there's no way you could make a substituent out of 9 hydrogens and 2 oxygens. It's impossible, okay? So that's one. Another one is that you notice that there's no aromatic signals in the IR, and also aromatic protons come out between 6.5 and 8 parts per million. So there's nothing up here, so not aromatic, okay? And we could also look at the carbon 13 and say, well, there's something with a high chemical shift here, but nothing as high as aromatic. So we would also say here, not aromatic. Okay, so there's no aromatic ring. So we've either got 2 alcohols or an alcohol in an ether. And where would we find the carbon-oxygen stretch for an ether? That would be somewhere around here. So could we have an ether? Okay, so now let's take a look at the proton. And keep in mind there's 14 protons. So we have H14, okay? Now, if we tally up 2 plus 2 plus 2, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so the integrations all line up. And you see that we have a singlet for 1 proton. So that has to be the alcohol proton, okay? And you notice that there's no other singlets that integrate for 1. So that tells you that there aren't 2 alcohols in the compound because there's no symmetry in the compound, or very little, because we have a total of 6 carbons. And look, 1, 2, 3, 4, 5, 6. So we see that there is no symmetry in the compound. And so if there's no symmetry in the compound and we only have 1 singlet that integrates for 1, that tells us now we know that we have an alcohol and an ether in the compound. Okay, so we have an alcohol and we have an ether in the compound. All right, so now we have the 2 functional groups lined up. Now let's take a look at our proton a little bit more. Okay, is everybody with me so far on how I figured this out? Okay, I looked at the proton, I looked at the carbon. Every carbon is unique. There's no symmetry in the compound. There's 2 oxygens. I've got to have an alcohol for sure. And I figured out the other functional group is an ether because there's only 1 alcohol in the whole compound. Okay, cool. So that means I have an alcohol and an ether. Well, as far as, chemical shifts for carbon, that is attached to an oxygen. So if you go into the table, and I don't have it here, no, I have chemical shifts memorized, but let me just double check here. The numbers that we give you for the quizzes. Just bear with me 2 seconds. Here we go. All right, so there we go. So in the table that you're given, what it says is if you have a bond to an oxygen, it's somewhere between 50 and 100. So if you have a bond between a carbon and an oxygen, it's somewhere between 50 and 100. So we'll put here 50 to 100. It varies from book to book, but this is what we're using for our textbook. So that means that all three of these carbons, excuse me, up here, these are all bonds to oxygen, right? This is a bond to oxygen, this is a bond to oxygen, that's a bond to oxygen. So that means we have a carbon that's attached to our alcohol, and then we have two carbons that are attached to our ether, right? So that takes care of three of them, and then there's three more of them that aren't attached to any oxygens, and you see those down here, okay? So we have three that aren't attached to any oxygen like that. So now what we're going to have to rely on a little bit is going to be the proton NMR. And if you look at the proton chemical shifts that we give you, we say that if you have an alcohol, it's between 2 to 5. So this is our alcohol here. Then we said if you have protons that are next to an ether. So I'm just looking at the thing that we give you. So yeah, I guess we don't give you anything like that. But we do know that if you have, let's say, a methylene and it's attached to an oxygen, right? The baseline for a methylene was 1.2, and then we would add 2.5 to that, which would give us 3.7 parts per million. And you notice that 3.7 parts per million is right here, and all three of these are close to 3.7 parts per million. So that means that these are all methylenes attached to an oxygen. So that means that we have to have a methylene attached to our alcohol. And that also means that we have two methylenes attached like this. So based off of these pieces, okay, we know we have this piece in our molecule and we know we have this piece in our molecule. So at this point, what do we have left? If we have C6H14, we've used up 3 of our carbons, so we have 3 carbons left. We've used up both of our oxygen, so those are gone. And as far as our hydrogen goes, we've used up 6, so that means that we have 8 left. So we have 8 hydrogens left. Well, let's see here. We have 1, 2, 3, 4, 5, 6, 7, 8. So sorry, I didn't count that up. 7, so we have 7 left. My mistake, because I forget the alcohol. There we go. So we have C3H7 left, okay? Now, where's that going to be? Well, we've got to have at least one methyl in our compound. So we have a CH3. So that we have a CH3. And you can see that it's a triplet. So that CH3 has to be attached to a methylene. All right, it's got to be attached to a methylene somewhere. All right, so we have to have something like that. And then what else? We have these 2 methylenes here, which are all split, okay, and it's very difficult to see. But if you take a look very closely, so this must be a CH2, and this must be a CH2, okay? Those are 2 methylenes. So far, we've got all this stuff set up. So then, if we take a look at this one on the right, it's got 1, 2, 3, 4, 5. So that means it's coupled next to 4 protons, or it's split by 4 protons. And this one here looks like it's, or maybe it's more, but 1, 2, 3, 4, 5. So that one looks like it's split by 4 protons as well, but it could be more, okay? I would say it could be more because it's very difficult to see what's going on right here. So as far as the pieces go, we would want to start putting these pieces together. So these are all the pieces for our molecule. We just have to put them together in some way that makes some kind of sense. And so the best way to put these together would be something like this. So if we have CH3, CH2, and then we have CH2O, CH2, like this. And then we have another methylene like this, and then we have our alcohol. Oops. Sorry, I put that methylene in the wrong spot. So if I move this over, oops, that didn't work. Let me just try and write it out here. So if we have, yeah, I should have put it like this. So I had those 2 groups reversed. So I'm just trying to color code it here, but it's actually making it more difficult for me. anyhow, so we have something like this. Then we have our ether like this, right? Then we have the last CH2OH like that. Now that seems to make sense to me, something that looks like that. So if you draw the bond line structure of the compound, it just looks like this. So we have something like this, and then we have two more methylenes, and then we have our alcohol. So that's the bond line structure of the compound. But if we just take a look at the splitting and the chemical shifts, you can see that it does make sense. So if we start with our proton and we annotate it. So I'm going to delete everything off of the proton NMR like this. So we'll get rid of all that. And what we'll do is we'll put A, B, C, D, E, F, and G like that. So obviously this one is going to be A because it's the only one that gives us a triplet. Now, as far as B goes, you can see that B is a multiplet, okay? But it's actually very difficult to tell how much it's split because it looks like 1, 2, 3, 4, 5. But to me, it looks like there's something buried under there because these two signals are overlapping. So it could be 6. And it actually has to be 6 because the second lowest chemical shift would be these two protons here, which are split by 5 protons, right? 1, 2, 3, 4, 5. So that would actually give you a sextet, okay? So then the next ones would have to be these ones because they have the third lowest chemical shift, and they're split by 1, 2, 3, 4. So it makes sense that you have 1, 2, 3, 4, 5. So those would be the C protons. There we go. So these must be the C protons. Now we get up close to the ones that are attached to the oxygen. So that means that these ones, and these ones are all going to be the EFG protons. Why? Because they're all attached to oxygens. So if we look at the splitting very carefully, the one that is the most deshielded is going to have to be is the did I label it wrong? Oh, I'm looking at something here. So A, B, C. Yeah, so the one that's going to be the most deshielded is the one attached to the alcohol, right? Because an alcohol increases the chemical shift by 2.5 parts per million. And so we see here that we have, it looks like a triplet. It looks like we have a triplet, and a triplet. So these are all triplets. Now, if you tried to annotate this and you mix them up, it wouldn't bother me too much because you see that this is going to give you a triplet, this gives you a triplet, and this gives you a triplet. The proper annotation is D, E, and F like this. But anyhow, again, if you mix those up, it wouldn't bother me one bit because all three of them are triplets and they're all attached to oxygens. So there we go. So that has to be the structure of the compound. So kind of an interesting compound in that you have an ether and an alcohol in it. All right. So that's my kind of slow problem solving there. But give me a thumbs up if you followed me on the stepwise solution there. Everybody with me on, or is there any questions about that one? It could be solved faster than I did it. I actually did it slower, which I think made it more difficult. But anyhow, hopefully that makes some sense. So let's move on to the next one. So this one here, it says deduce the structure of the compound. They give you a molecular formula, C8H10O. It exhibits this this IR, so they give us an IR, they give us a proton, and they give us a carbon 13. And as far as low-hanging fruit in the in the IR, let's start with the molecular formula. So we have C8H10O. Did anybody figure out the HDI for this compound? Could anybody tell me what the HDI is? Sorry, Isaac, I should have put the G proton here. And the D is there. There we go. Does that help? Yeah, because I forgot this one here. All right. So did anybody get an HDI for this compound, C8H10? So if you have 2 times 8 gives you 16, plus 2 is 18. 18 subtract 10 is 8, divided by 2 is 4. We have an HDI of 4. What did I tell you guys to always look for if you have an HDI of 4 or greater? So if your HDI is greater than or equal to 4, what should you, exactly. So you ask yourself, is this aromatic? So Jenny, is this an aromatic compound? Anybody figure, is it aromatic, yes or no? Just by taking a quick glance at the proton and the IR, would you say it is an aromatic compound? And it's not a trick question. Yeah, absolutely. Right? You can see you have aromatic protons here. So it's definitely aromatic. All right. And then in the IR, if you look between 1600 and 1450, something like that, you can see you have carbon-carbon double bond stretching here. So this is carbon-carbon double bond stretch, aromatic. And we also have some overtones here. So these are overtones. And then if we look above 3000, which is kind of hard to see, so let me get the ruler out here. If we draw a line here, all right, if we look above 3000, yeah, this might be some, sp2 hybridized carbon-hydrogen stretching here from the aromatic ring. Anyhow, and then we also have an oxygen in this compound. And so if it's not so what else can we say about the functional groups? If the HDI is 4, an aromatic ring has an HDI of 4, right? This has an HDI of 4. So if we have an oxygen and there's no alcohol here, right? So it's not an alcohol. What is the functional group that must be in this compound? The other functional group besides the aromatic ring. We've used up all our HDI, so there's no carbonyl. So could anybody tell me what the other functional group must be? All the HDIs are used up in the aromatic ring. It's not an alcohol, but there's a functional group that has an oxygen in it. Exactly. So we have an ether. It has to be an ether because an ether has an HDI of 0. So there you go. So that means what? It means we've got an aromatic ring, we've got an ether, we've got something like this somewhere. If we look at the proton, we've got 4 protons in the aromatic region. And we've got a singlet for 3 and a singlet for 3. So if we have a singlet for 3, that has to be a methyl, and this has to be a methyl, right? So, I mean, you can see it's kind of starting to come together here. Now, in terms of the carbon, we have a total of 8 carbons in our formula, C8, but we have, if I label these, we have 1, 2, 3, 4, 5, 6 signals in our carbon. So it says there are 2 unresolved lines at 130. So what it's saying is this, is you count it like this. You count 1, 2, 3, 4, and 5. These are 2, they're unresolved. It means they're so close, they're overlapping with each other. 6, like that. Does that make sense to everybody? Like they're so close to each other. Okay. All right. So now that we have that, so if you were to put letters to it, you would say A, B, C, D / E, F, like that. So it's a total of 6 signals. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So if we have 6 signals and we have 8 carbons, it tells us that there is some symmetry in the compound. There has to be some symmetry in here. All right. Are you guys ready for one more fact that I haven't gone over with you yet? I know it's something new, but you might have seen this in the lab if you're taking the lab with Mr. Geiger. When you're in the aromatic region, so let's say, you're somewhere in the neighborhood of 7 parts per million. If you have a doublet that kind of looks like this, and then another doublet that's leaning in like this, so you have a doublet, and they're kind of leaning in towards each other like this, okay? in the aromatic region. This one, if one integrates for 2 protons and the other one integrates for 2 protons, and we see that right here, it means something. It means that the aromatic ring, it's what we call para-substituted. So what is para-substitution? It's when you have an aromatic ring and you've got 2 substituents on opposite sides of the ring and they're different, X and Y. Okay, this is called I'll just write it up here. Para-substitution. Okay, and this is a rule in organic chemistry in proton NMR. If you have 2 doublets that are kind of leaning in towards each other like this in the aromatic region, it means you've got an aromatic ring with 2 substituents on opposite sides of the ring, and the 2 substituents are different. Okay, it's called para-substitution. So now what do we have? We have only one way to put this compound together, literally one thing. Okay, we have our aromatic ring, which looks something like this. Then we have an ether. Okay, and we have 2 methyl groups. So that means we have to have 1 methyl group here and 1 methyl group here. It's the only possible way that we could put that together. So this is called paramethyl anisole. The name is neither here nor there. But if we label these A, B, C, and D, so the way you would say put this together is you'd say these are the A protons here. These are the B protons because they're attached to the oxygen, so they're more D-shielded. And as far as D and C goes, well, the D protons are going to be the one closer to the oxygen because they're more D-shielded, and these would be the C protons, like this. As far as the carbon goes, okay, so if we look at the carbon, we'll redraw the compound. So, and this one might be a little more difficult, but we'll try our best. So let's just move this over here. So if we put our ether up here and put our other methyl group down here. Okay, so let's see if we can label or annotate this one. So A is the carbon that is the least D-shielded, followed by B, right? This one is attached to oxygen, and it comes somewhere between 50 and 80, okay, some are 50 and 100, something like that. These ones are going to be aromatic, okay? And then we have F, this one up here, which is got the most D-shielded. So this one has to be F here. And as far as D and E and C go, well, it says there's 2 lines that are unresolved at 130. So my guess is that one of them is really tall and one of them is really small, okay? Because normally, like I said, if you have twice the number of carbons, it's going to give you a higher peak. So my guess is that D is, we'll just put D or E, but D is going to be these ones here, and then E would be here, and then C would be these ones here because they're less D-shielded. Again, if you get that, close, it's good enough. It's probably good enough for me or for Mr. Geiger. But there you go. All right, so we were able to solve that one. So again, you'd call this compound paramethyl anisole is the name of that compound, which again is neither here nor there. But there we go. So those are a few of the questions from Klein. All right.